to a carbon-carbon double bond. So the typical reaction is, let's assume that you have the following alkene, and then you use either Br2 or Cl2 in the presence of an organic solvent, typically carbon tetrachloride, or chloroform, CaCl3, this type of organic solvent, and both halogens of the Br2 or Cl2 molecule will add on to the carbon-carbon double bond, converting it to an sp3 hybridized carbon. So this would be the product. Now, this reaction undergoes a specific mechanism which it goes through a halonium ion. So it goes through a halonium ion. In this case, of course, it would be bromonium ion. And what is a bromonium ion? In which case, the intermediate is actually a three-membered ring system where Br would be attached to both carbons, and the Br is actually positively charged. So this is the intermediate, which then is opened up by attack from the Br minus, which is formed during the reaction. So the Br minus attacks and opens up the ring, generating the final product. And as a result, now Br minus cannot approach based from this side. This is blocked by the three-membered ring that bromine created. So it comes from the other side, and therefore that addition is anti-addition. Okay, so because of the anti-addition, now in this particular case, you wouldn't see any difference because two bromines are added, and you have free rotation around carbon-carbon single bond. However, if it is a cyclic molecule or where it is restricted, then you will see that addition being anti. For example, in this case, if you treat it with Br2 or Cl2, but you are going to get a specific stereoisomeric product, which is like this. Now, obviously that means that if you had a six-membered ring system, that would generate, in this case, a cis dibromide, a trans dibromide, and as a result, they will end up either dihydroxyl or diaxial. Okay, so obviously this is unstable, so even if it forms diaxial, that will actually flip to generate a dihydroxyl. So there is a restriction as to how this reaction goes. Another thing about the bromonium ion is that the hypothesis indicates that this is 4. Okay? And an alternate structure could have been that it is attached to the carbon, and as a result, if it is only attached to one carbon, is it possible that this is an intermediate and not this? And that, in fact, one of the ways you can examine that is to see that what would be the transition state in a molecule like this. The Br bromonium ion involves a small positive charge in the carbons, whereas this is an entire one full positive charge polonium ion intermediate. So for hydration reaction, in the presence of oxide acid, there is huge rate difference. If you carry out this reaction to add hydrogen and OH to the across the double bond, then the rates, assuming this is 1, this is greater than 1 million, and this is greater than 100 million. So the rates are enormously different. Why? The reason is the stability of the carbon cation, because in each case, the first stage which generates formation of a cation, this is primary. In the second case, it is secondary. The third case is tertiary. Because we're just following the Markovnikov's rule that hydrogen is added to the carbon with maximum number of hydrogen, generating the carbon cation. And because of the involvement of the carbon cation, whose stability depends enormously on how substituted that particular carbon cation is. This is primary, this is secondary, and this is tertiary. There is a huge rate difference that we see. In the case of the bromination of this reaction, the rates, on the other hand, for the same, let's say this is A, this is B, and this is C. So the rates for the halogenation reaction is typically is 1 to 61 to, this is about 1500 or so. No, this is about 5,400 rate for the bromination. And mechanistically you can rationalize that because the rate is better, but nowhere near this much, because the cation is not completely generated on the carbon. Because of the bromine being positively charged, small positive charge would be expected on the carbon, which would therefore be stabilized by an empty group. Okay. But the difference is not as enormous as we have seen in the case of hydration reaction. So again, the halogenation reactions happen with bromine and chlorine. Chlorine is faster than bromine. Now, a variation of this reaction is that you can also carry out the reaction in the presence of water. If you do that, then a different product is generated. So let's assume that you use the same reaction, Br2, in the presence of water rather than carbon tetrachloride. In In that case, what happens is you add one bromine and another OH. And furthermore, the stereochemistry is still anti, or in this case, one would be, and this one would be dash. Now, the intermediate is the same in both cases. In this case as well, you form the bromonium ion. Which is then opened up by the attack of the water molecule. And the water attacks one of the positions and giving rise to this product, which is again would be like this, and then subsequently another molecule of water can pick up the extra proton, giving rise to the final product. Okay. Now, one of the interesting thing about this reaction is that if you have a substituent across the double bond, then it turns out that, let's say, if you have an alkyl group here, then the same reaction would exclusively generate not only the anti-product, but the fact that the OH is going to go to the more substituted carbon. So this specific stereochemistry as well as the radioselectivity is seen. Why? Because when you look at the intermediate that is generated here, which is the bromonium ion, this is the intermediate that is generated. And now assume where you would get a more stable cation if you had to break the bond between this carbon and bromine versus this carbon and bromine. If you break the bond here, when the bromine is attached to the top carbon, then you get a secondary cation. If you break the bond here, you get a secondary cation, but if you break the bond here, then you are going to get a tertiary cation. As a result, that is a preferred way of breaking the bond, and as a result, you end up with the OH group attaching to the top and not the bottom. So there is a very clear sequence of how this reaction proceeds through the bromonium ion on the chlorine. And again, chlorine does exactly the same thing, same specificity as well. Okay. Any question on this one? All right. A couple of other reactions that we'll move through. Epoxidation of alkenes. Okay, epoxides are three atom system, cyclic system, where one of them is occupied with an oxygen. So these are typically epoxides. And epoxides are relatively stable compound, but they can participate in many reactions. That's why there is a lot of interest in there. The epoxidations are carried out with peroxy acid. So carbon-carbon double bonds can be converted to epoxides by peroxyacids. What are peroxyacids? So we haven't actually discussed much of the organic acids, even though in the very first chapter we talked about acids and bases. Now, the carboxylic acids are one of the most common group of these are the carboxylic acids. What are could be a variety of different species, but the actual acid group is COOH. So these are carboxylic acids. And there are lots of common acids like acetic acid, which is present in vinegar, is an acetic acid contains the RS levels. The formic acid, which is present in like the sting of the ant, that's what they inject and that converts. That is essentially a hydrogen. R is the hydrogen formic acid. So these are some of the very common carboxylic acids. Now, the peroxyacids are relatively unstable, but they have an extra oxygen. So peroxyacids typically have R joined with COOH. An extra oxygen. And that oxygen is really very easy to transfer to carbon-carbon double bond. What really happens is that if you have a carbon-carbon double bond, and regardless of which substituents you have, and you place the so let's say you are using peroxyacetic acid. What happens is that in this reaction, essentially this becomes the oxygen is transferred to the, so this is the epoxide that it generates. And so it's a very easy reaction, yes.
Can you slide it over?
So peroxyacids are relatively easy to transfer one oxygen, which in turn is converted to a carboxylic acid. They are converted and epoxide is converted. So as for example, if you use the same one that we used before, so this is a fairly straightforward reaction in which we can get an epoxide like this. And of course you have the option to write it either this way or if the structure is correct. What was that? Okay, in this case, because the oxygen is attached to both carbons, typically they come from the same side. So they will be both either dash or OH. This is actually a C addition to the double bond. Okay, so and let's move on to the final reaction. This is ozonolysis. Ozone, as you know, is three oxygens joined together, and therefore one of them have a double bond. This oxygen is positively charged, the other oxygen connected to it is negatively charged. And of course, you can draw another resonance structure of this, where they switch places. So now the ozone can be added to carbon-carbon double bond, forming what is known as unstable ozonide. Okay. So again, let's assume that you have a carbon-carbon double bond. You treat it with ozone. That would generate what we know as ozonide, where you have a 5-membered ring system generated such as this, ozonide. And then that is relatively unstable and can be broken into two carbonyl groups by in the presence of water. And if you this, so two carbonyl groups are generated from these two carbons. In other words, let's assume that you start with something like this. And in the first step, you treat it with ozone. In the second step, you actually need a reducing agent because it generates hydrogen peroxide, and they would oxidize the molecule further, and therefore you need to destroy the hydrogen peroxide. Usually zinc is used, zinc with water, or dimethyl sulfide. And by doing that, what happens is you would really break the bond between this carbon and generate two carbonyl compounds. So CH3, CHO plus CH2O. This is formaldehyde. So essentially, anytime you see carbon-carbon double bond, you can break the bond and add a double bonded O to both sides. That's essentially what the net result is of the ozonolysis. And ozonolysis, as you will see in the next class, is a very useful technique for many of the structural characterization, because you can, in each place you have a carbon-carbon double bond, you can break it and add a oxygen there. And therefore, the position of the double bonds are figured out this way. That this used to be the method of choice before the spectroscopy technique became very common. Any question? There's a bunch of reaction I want you to go over them during the weekend, and then we can again review them on Monday. But I want to go through some of the problems, the handout that I gave you, that essentially is from the back of the chapter. So a couple problems, let's try. This is something that we already discussed. Okay. So this is the this is problem 6.39. Okay, so the first problem indicates you add HBr to carbon-carbon double bond. The HBr, particularly I'm getting to the point of no peroxide, is very important. This is what we actually learned previously, that you add according to Marconi constant. When there is a presence of peroxide, it follows a radical mechanism, something that we excluded. Okay. So I won't ask you any question. Anytime in this course, if I ask you HBr addition or HCl addition, you follow the Marconi constant. And that's what is going to happen in the first question. Okay. So again, there's no difference between them, so you can add the H and Br to any one of them. It doesn't matter because there is no, you can't really apply the Marconi constant. CH2, CH2, CHBr, and the rest of it remains the same, CH2, CH2. So that will be the product generated in this reaction, right? And you can write the Br on this carbon, it doesn't matter, it's still the same thing. The second problem is not included because it includes peroxide, which actually adds to the anti-Marconi compound, but we haven't covered that. The third problem is 2-tertiary butyl 3,3-dimethyl 1-butene. So this is 1-butene. And this is T-butyl group, and 3, this is 1, this is 2, 3,3-dimethyl. So this is the structure of the molecule, and then we are carrying out diborane addition between 6 followed by H4 OH minus, and that we know adds in an anti-Marconi compound, right? H and OH are added. That is the net result. So if we do anti-Marconi compound, we have to add the OH to the first carbon, right? So we add here OH, and it's also scene addition, but in this case stereochemistry doesn't matter. And so the H will be added to this one. The rest of it remains unaffected. So that would be the product generated from this. The next one is also easy, but in this case it's a scene addition. So you have to show the stereochemistry because it's a cyclic molecule. And so we can draw the methyl groups on the same side. And now H and OH would be added from the same side. And of course, you can do either way. You can write the methyl dash and OH and H as OH. So Br2 in chloroform. This one again will be added to both this carbon-carbon double bond. This is again, you can ignore the stereochemistry, CH2Br, and then CBr, CH3, CH2, CH2, CH. no different except that now you have water present, therefore OH has to go to the more substituted carbon, right? That's what we discussed, and therefore the first one is more substituted. So CH3, C, and that's where the OH would go, and CH, Br, CH3. This will be the product. Now this one you can recognize this is peroxy acid. You have CO, OOH, and therefore this will form an epoxide. C, here it is epoxide, and then you have two methyl groups and two methyl groups. The ozonolysis breaks the carbon-carbon double bond, so you can see this one is going to generate two carbon groups. Yeah. What? Oh. All right. Okay. So the G is, this one is again chlorine with water, and again you need to form the chloroniamine and open it so that it opens to generate the positive charge on the carbon with the metal. So that's where the water will go. And therefore the product from this is, so we need to add in anti-orientation. That's another important one. That you, let's say methyl group is OH and the OH is dash. Therefore the chlorine would be OH, the other one. And the H would be dash. So the chlorine and OH is an added in the anti-orientation. That's important to show inside the code. Okay. Any question about these reactions? They are fairly straightforward. You just need to learn the very basic. And on Monday, I'll give you a handout summarizing all that. Next problem asks you to figure out bromine reacts with methanol according to the equation. Just like water, the methanol OCH3 group is added to the carbon group more substituted. So in this case, it shows the Br addition to one carbon and OCH3 addition to another one. So now the question is, if you carry out the reaction with 4-butyl cyclohexene, although the structure is not exactly like this, let me draw it this way, it's easier. So they're asking you how they would be added to this. Okay, because it's a cyclohexene, it doesn't really maintain a clear tear form. Nevertheless, it's easier to draw it this way. So you can see the product form. Now, the bromine and the methoxy group, their relationship is going to be what? Trans, right? So if they're trans, then we need to make sure that there's actually a methyl group already there. They actually named the compound wrong. It's 4-butyl methyl cyclohexene. That's what that shows. So it's important that you add the OCH3 group to that particular carbon, right? So the methoxy would go there, and the bromine is going to go to the other carbon. So the bromine will be added here, and the OCH3 will be added there. Also, the relationship is going to be trans. So either they will be diaxial or diequatorial, right? And if we examine this, the only one that corresponds to that is this one. Because this is where the bromine and the methoxy are both axial, which is trans relationship, and then the methyl and the dibutyl group are in equatorial. Any question?